Sure.
Yeah, thank you for recording, Patrick.
Okay, so do you see my screen correctly?
Yes, everything's
Perfect.
fine.
Perfect.
But I think we don't see your camera if you have it on or not.
Oh, maybe I didn't click on it. When
You
I
don't
was...
have to, but I guess it would be nice.
No, it's okay. It's okay. I just didn't allow it accidentally when connecting to Zoom. Okay, so hi everybody.
Yeah, the floor is yours.
Okay, so as we can see from the title and as Standa announced, and as you have read in the abstract, this is the second part of the contribution to the theory seminar. So I'm happy that I can share with you what I'm doing. A lot of what you will see is still a work in progress. So don't hesitate to ask any kind of questions, and also expect a bit that I don't have answer to everything, but definitely questions, comments are more than welcomed. So this part is a application of the formalism that we have seen in the last week. And in the beginning, we will just quickly go through the basic tools that we developed, or rather described the last time. And then we will move forward to examples and how it can be used with respect to small amount of variational problems, or rather inverse variational problems. And also I'll give a sketch of a possible generalization of these ideas for more than one scalar field. But this is really mainly this part is a work in progress, because some things works nicely, but some other things does not work so nicely in this context. So let's see. And at the very end, I will just show how a multisymplectic forms can be derived from effective forms of given equations. And I will not go into the multisymplectic geometry itself, although it's quite interesting. But this is also something I'm not completely sure whether I could give really reasonable answers and description of what is going on. Yeah? But definitely, if there is somebody who is interested in multisymplectic stuff, then we can discuss later on, and whatever any participant would be interested in. So let me begin. If any of the notations are not clear, just ask immediately, please. So overview of part one, then application to inverse variational problem. The application is not that much about finding the solution, but rather, as I said the last time, rather showing quite efficiently that there is not a solution to a given equation with respect to inverse variational problem. We will see examples. First example will be very simple, almost trivial. Everybody knows this, but I will just show how computationally the stuff works. And then the other examples are computationally a bit more involved, not that much about the difficulty with computations, but there is simply more terms as the dimension is higher. Then, as I said, I'll give a brief idea of how it can be generalized to two fields, and at the end, the multisymplectic forms. Okay, so what do we want to do? We want to work with concrete equations and use the apparatus described the last time to show that both Heaven equations of Plebanski, Grand equation, and Husain equations are not variational, in the sense that there is not a first order Lagrangian for which those equations would be Euler-Lagrange equations. And everything else is more or less what I said. I remind you that all our considerations are local, so we are not dealing with global issues at all. Okay, so just a brief overview. We are working on the first jet space. On the first jet space are differential forms that we are working with, and then the differential forms are pulled back down on the base manifold M to provide a description of the equation itself. So recall that J1M is a bundle over M with a bundle projection, and the projection itself is given by the first prolongation of this simple projection n times R to M. Recall also that every function over M, every real scalar field, those are the objects we are interested in here. Those are the objects for which the equations will be considered. Defines a section from M to J1M, and in local coordinates it looks like this, right? So if you see coordinates Q, U, and P, those are coordinates on J1M. And if you take the section, it's simply substitution for U, you substitute phi, and for P mu, you substitute phi mu, which is a directional derivative of phi with respect to base coordinate Q mu. So the main structure that is on J1M is the Cartan distribution, which is described by this differential one form called contact form, or in the context of J1M, we can also call it Cartan form. I remind you that this case of having these Cartan distributions are on all jet bundles, but in the case of J1M, the Cartan distribution is one codimensional, and thus it is also a contact structure. And that's what we are using here. And the splitting of the tangent bundle of J1M, so every tangent space of J1M can be split into this direct sum. So once you pick a contact form, then you can split the tangent bundle of J1M into its kernel and kernel of its differential. This is this one-dimensional space I was talking about, and this is the distribution itself. Now the one-dimensional subbundle is spanned by the Reeb vector field. This is the main condition, yeah, that this field is given by the fact that it's living in the kernel of DC, and also just a normalization condition, so we have this nice coordinate expression if we choose coordinates such that the contact form is in this form. Okay, and then, as was said the last time, the DC, the external derivative of the contact form, is two form which over the Cartan distribution is in fact symplectic. So that's those are the starting points. Now we introduce some operators. So we have the bottom operator. This is just a contraction with a two vector field which is dual to omega. And now duality is, I mean, in a similar sense as for one forms, but in fact, how we determine this x omega is that we simply consider duals to the forms, to the one forms from which omega consists. Right?
What is omega?
And omega is the symplectic form.
So that was equal to DC?
Yes, exactly, this guy. Okay. Yeah, at the end of the slide. Yeah.
Okay.
Mm-hmm. And once we have the two vector field, we can simply consider the contractions with arbitrary form, and so that everything is consistent. If the form to be contracted with is 0 on one form, it's the definition simply says bottom of such a form is 0 automatically. Then we can consider the Monge-Ampere operator, and notice the operator for a fixed form omega, which is a n form, and n here is the dimension of the base manifold, so the dimension of M. So if omega is an n form, and we fixed some n form, then the operator takes phi, and the result is this n form on M, right? So this guy omega is an n form on J1M, and there is many n forms on J1M because J1M, if M is n dimensional, J1M is 2n plus 1 dimensional, right? So there are plenty of such guys. But once we pull it back down on M, everybody knows that the top forms are only one dimensional, right? So this operator, if we put it equal to 0, defines an equation, and such an equation will be called Monge-Ampere equation. Yeah. If this guy, or equivalent to this guy, is put equal to 0, we have an equation for phi. And that's the main idea of describing certain partial differential equations with differential forms on J1M.
How does it look in local coordinates?
This guy?
Yeah.
Well, depends. We will see in the examples. Depends on how you choose omega, right?
Well, a generic omega.
Generic omega might be quite complicated. So but you will see in the examples. You will see in the examples. It's I mean, it's very intuitive, yeah. But for a generic omega, you will get expression with bunch of terms which doesn't tell you that much. You see? But just wait a bit. Okay, so projection operator. This projection operator just allows us to take arbitrary form on J1M and project it on subspace of forms over J1M which are degenerate along the REAP field. And this is required in order to be able to have, why we want to project forms on subspace of forms which are degenerate along REAP field. Because on this subspace, the wedging with omega is isomorphism, because omega is there non-degenerate, right? So we can do symplectic calculus with omega with these forms. Yeah, but notice, for example, that if you take form which already is degenerate along the REAP field and you consider the exterior derivative, this condition is not preserved. So then we need to consider the projected exterior derivative, simply composition. This is the classical guy, and this P is defined here. And also we use the Lie derivative along the REAP field. So once we have all these operators, we can define the Euler operator. And this Euler operator, what it does is, whenever we consider a variational problem that is coming from, let me say differently. Consider first order Lagrangian. I think I should, this term density, just forget it. And consider this guy. L is a function on J1M, so it depends on Q mu, U, and P mu. And beta always will be this combination of dq1 wedge up to dqn. Okay. And then if you consider the Monjumper, then what do we do then? Take L beta, apply E, Euler operator on it, and then construct the Monjumper equation. And this is an equation of phi, as I said, and it will be precisely the Euler-Lagrange equation for this L, but understood as a function depending on Q mu, phi, and phi mu. Okay, so this is just good point to say here that we do not distinguish, only in one case, we do not distinguish L, which is a function on J1M, so it depends on Q mu, U, and P mu, and it's pulled back down to M along J1 phi.
Oh, okay, maybe what I don't understand is, what is a pullback of a J1 phi?
It's just so simply said, it's just a substitution. Wherever you see U, you put phi, and whenever
then
you
I
see
understand, but how do you take the pullback of it?
Of what?
So you say J1 phi star, which I assume is pullback
of L beta, right?
On omega. So how do you do that?
So take, for example, omega equals L beta, right?
No, let's go up to the first ampere operator. How is that defined?
Well, you can consider pullbacks of arbitrary form, right?
No. How do you do that? Well, I only understand how to take pullback on a function. How do you take pullback on J1 on?
So you see, J1 phi is a section.
Yes.
From M to J1M, right?
Yes. And it has 3 coordinates. Yeah.
No, but it doesn't matter what kind of coordinates it has, but it's a mapping from M to J1M.
Okay, and what do you do that when how do you plug that into?
And if I take arbitrary form, K form here on J1M, then it can be pulled back to forms on M, right?
Why? How?
Well, you can do pullbacks of this is just a smooth mapping, right?
How does it work?
It works simply as this way. You take something which is in these coordinates, yeah?
I understand that.
And then you substitute, for you substitute phi.
That I understand, that part. But how do you then take the pullback of that on omega? What operation is that?
The pullback operation. I don't understand the question.
Yeah, well, I want to understand what's written.
So for example,
on the next side, on the next page, what does this mean?
This guy.
This guy, yeah.
Yeah.
Radek.
Yes.
Maybe you should explain that. That's where that's what probably explains everything. How you pull back the DP guys? What?
Yes. So if you go, but this follows from the so maybe I'm too quick about it, yeah. But this follows from the property of pullbacks, yeah. Pullbacks commutes with exterior derivative. If I, for example, take this omega, yeah, and I want to pull back two form, it doesn't matter whether it's a K form, two form, one form, it will work all the time the same, right? It commutes with the exterior derivative. So the question is, how do I pull back Q and how do I pull back P, right? If I pull back Q, it's the same guy. If I pull back P, it's substitution for phi mu. Then, if I pull back dP mu, then it's the same thing as pull backing P mu, which is a function, and then computing the exterior derivative, because exterior derivative commutes with pullbacks. And it's also distributive along, with respect to wedge product. So sorry if I didn't say that the last time as well. I assumed this to be clear, but I'm very, very sorry if this was a part of confusion.
Yeah, it probably was.
Does it make sense now? I mean, maybe I should have introduced examples in the first lecture, at least simple one.
What I find a little confusing, but that's maybe me not understanding stuff, is that you want probably things to be invariant under change of coordinates, right? And Q and phi, they're nice, and D works okay on them, but phi should get multiplied with Jacobian upon changing coordinates, right? If it's like a proper coordinate representing the partial derivatives of phi. And then what happens when you pull it back? When you make D out of it, it's not really invariant under that change of coordinate transformation, right? What happens there? Or you don't assume that there's a invariance under change of coordinates?
Oh, good question. I wasn't thinking about this thing, yeah, about invariance with respect to change of coordinates, but it's a good question.
Andrea, why wouldn't it be invariant?
Because I think what Andrea means is if you change P mu similarly as phi mu after coordinate changes, then you apply D.
It's like D, right? D is already like a derivative, and if I apply two derivatives, it's not transforming as tensor. That's what I mean.
Yeah. Well, dP mu is not invariant. Yeah. Mm-hmm. But you always have that contracted with some function which transforms with the opposite index. Every form you have is like.
Yeah, but if there's D in a way, then you're screwed, right? Because I understand that I can have form with indices and stuff, and some of them will contract dP of something, but dP, the P is not invariant, right? So D on it doesn't transform as tensor, and even if that coefficient of that form transform as tensor, then then I'm screwed. Do you see what I mean? Or
yeah, but I would need to write it down. Whether I understand.
Like having
exactly.
like, you know, just like t and function of f of t and first derivative of f of t, right? Then I can, the d of f of t is not a tensor, right? So I can't really, I mean, it's fine if you.
So once more, d of f of t is not a tensor.
Just like the simplest thing, right? Mapping from R to R3, where R3 has t, f, and f prime coordinates, right? That there will be my jet extension of, you know, of first order. And then I'm saying, like, if sure, I can write down some three one form on those three coordinates, but if I perceive them as t, f, and f prime, then f prime is already like a tensor thing, right? So I can't apply d on it. What do I do? I can do some covariant d, I guess, but that's extra structure, right?
Yeah, I understand. I think I understand what you mean. Yeah. But in fact, I don't need to do this to do this, right? Do I?
I think it's the advantage of the jet formalism that you
yes,
don't
exactly.
Treat,
you don't have to do that.
Treat the third coordinate as a derivative. You treat it as a new independent
Variable.
coordinate. So instead of having like n coordinates, one function, and then n derivatives of the function, you have 2 plus n basic r coordinates. And then
okay,
after you've done your calculation, you can identify them.
Exactly.
But then I'm. Is that consistent? I mean, I understand that I can perceive them independently, but when I actually introduce that, when I actually identify them with f and f prime, is it consistent? Consistent with that? Because suddenly they get that weird transformation, right? Which before they didn't. So maybe it's fine. Maybe I'm not.
I think that transformation rules are somehow encoded in the derivatives of the jets of the sections, if I remember correctly. That they are equivalence classes of. Oh, yeah. I think
Well, yeah. But it's a good question. It's a good question. I think I'll need to write it down, and maybe we can discuss later. Yeah, because I cannot say how the transformations rules comes down. But I understand that what you mean is that the square of the square diagram would not be maybe commutative if we consider the operations as Ondra described it.
Okay. Yeah, that okay, but
it doesn't. No, sorry.
Okay, so I guess I have learned pullback only for functions and diffeomorphism and so on. So I don't understand how the other how you can pull back when you have this coordinate here with J1 phi. What that actually means.
What means what? Once again.
I mean, I might be saying the wrong words, but I simply don't understand what that mon ampere operator is, the definition.
So let me skip to the example, right, immediately, and we can see whether things make sense if we see them.
But it's already used in for instance for the Euler-Lagrange equation there.
Yes. Exactly.
Can I maybe try to answer that?
Yeah, sure.
I don't know. I'll try. Oh, Patrick, can you, or I don't know if Radek or Patrick has to do that. Can you allow annotations on the one who shares the screen? Because I can write
yes, got it. Enable annotations for others. I think now it's possible.
You can write the formula, I guess. I don't know if this is what you're asking, Klaus, but so I have form omega, let's say on J1M. So this would be form on J. Oh, wait, Okay, it doesn't work now. Arrow, eraser, formula, draw. What? Okay. Sorry. I clicked on something, yeah. So that would be something like A, sigma. Oh, I can't erase. I see. That's the problem. Draw D, Q sigma plus A. Yeah, 1A du plus A sigma I D P. Oh, we don't have any I, right? That would be dp sigma. Yeah, sorry. I should put this one down, this one down.
Never mind that. That's
Yeah, never mind. Yeah, sure.
Never mind.
Yes, so this lives on J1M. And let's say now you have phi that goes from M to J1M. So you would have something like this, M. So you have a section here, then you have your forms here, and you can pull back in the opposite direction. So J1 phi star omega would be a form with the same coefficients, but on M. Yeah, so well. Yeah, so this thing is invariant under the. Yeah, this thing would be the same.
Right, that's the same guy.
But you would have like something like this, that you want these coefficients to. Yeah, so these would be like functions on the jet space, but you would want them contracted with this phi.
Okay.
Composed, yes.
Oh, right.
The Q sigma. Yeah, then I'm not that sure what you would do with the du.
Yeah, U is phi, right?
Oh yeah, that's
so
true.
The pullback of U is phi.
Yeah, you're right. So that would be just the. But does the phi make sense?
Sure, the phi makes sense as well. Phi is nice.
Oh
function.
yeah, d phi is d phi
because
sigma.
Right?
Sigma, because the only one forms you have on M are dq sigma, right? So you want everything in dq
and
sigma.
dq sigmas, right?
And here you would just have a sigma q dot, right? Because p would be like, well, no, not q dot. No, yeah, I don't have one. I would have here something like this. So d phi sigma dq nu, something like that, from pullback of this.
Exactly.
Right.
But phi sigma now is actually a derivative of phi in the direction of q sigma. Phi sigma is not it's another function. It's like you have just one field phi, right?
Oh yeah.
You see? So phi sigma means del phi over del q sigma. And that's what you need to exterior derivative again.
Yeah, then I have something messed up with the indices, I guess. Because yeah, I have only one phi, which has one index, right?
Right.
Yeah, it's just phi with two derivatives on it, right? No.
Phi. So simply
phi. One contracted with Q and one with A.
I do have two derivatives here.
Right, exactly.
Yeah.
Sigma is for the A sigma index, and Ni is for dq Ni index. Exactly.
I guess this also answers my question or my confusion, because, well, you don't really want this to be invariant under all coordinate transformations on the jet space, right? You only want it to be covering under those base induced coordinate transformations, and that's fine because those vanish on the contact form, right? So that's the only thing which would screw this up. But if you're not mixing phi's with the Q and doing coordinate transformations on Q, then you're fine, and this is all covariant.
If you are not mixing what? Once again, please.
What?
If you are not mixing.
I'm saying you don't really want this to be invariant under all the changes of.
Oh yeah, sure. Of the diffeomorphism over J1M, right? Sure.
Even though, yeah,
right.
It's still a little weird because the last term, right? The last term, if I change coordinates,
maybe this is not right. Maybe
yeah,
there's a derivative maybe on the A.
No, it's not.
No,
it's
that
not.
seems
Okay.
right.
This is correct. But
Okay.
Simply A sigma is the same as you write in the very beginning. A sigma circ phi, right?
Yeah.
The pullback. And what I understood on Drament is if I change this guy, right, then whether the whole thing will be again.
Yeah, because
but I think it will be. Yeah, but
no, it won't.
It won't,
because it's second derivative on function, right? It doesn't transform tensorially.
Yeah, you want to have the special class of transformations,
Yeah.
But this anyway doesn't accommodate like a relativistic theories, right? It's only for non-relativistic, where it will. So yeah, it will be fine on like Poincare-like symmetries because they are of first order, and the non-tensorial bit will disappear, so it's fine.
Yeah, it's not really about relativist. You mean whether it's rigid, affine structure or not?
Yeah.
Okay, that was helpful.
Okay. So sorry that I didn't introduce this the last time. I thought it's well, unnecessarily assumed that it's known. So sorry for that. Okay, so that's now it is clear what this operator does. Is it? In the case of a general N form or K form.
Yeah, I guess because we just did one form and then wedge
exactly
with respect to.
Exactly. Then we use the properties of pullbacks. Okay. So I proceed. Okay, so we also introduced. Still, we are in the overview of part 1, but this is the last slide. The key notion was the effective forms, and those are two conditions for a form to be effective. Contraction with the Reed field must be 0, and bottom operator, which is contraction with the dual to symplectic form. Yeah, this guy is 0 as well. Okay. Example: first order Lagrangian is effective. Yeah. Locally, this operator looks like interior product with a 2 vector, which is del Q wedge del P. Okay, so that's how this operation looks like in local coordinates. And the key theorem is that every K form which satisfies this property can be decomposed as this sum, with the important fact that this omega E is a uniquely given part and it's effective. So to every form, I can find a unique corresponding effective part, right? And this form and this form will produce the same Monge-Ampere equation. The Monge-Ampere operator doesn't see whether I have this form or this form, because this guy contains omega, and omega pulled down along J1 phi is always 0, because omega is the exterior derivative of the contact form, and the contact form is precisely that form which when pulled back down along arbitrary J1 phi is 0. Yeah, so just see the coordinate expression of the contact form is this guy. And if you use the rules that were annotated on the slide just a minute before, you have d phi minus the pullback of C is d phi minus derivative of phi in the direction of Q, dq of Q mu, dq mu. Yeah, so it's exactly 0 for every phi. Okay, so then also omega as an exterior derivative of this is always 0. And whenever I have a form which contains omega or C in it, is wedged with it, is 0. But that was described in quite a detail in the last part. So this guy, Monge-Ampere operator of this guy is 0. And thus omega and omega E gives you the same equation, the same Monge-Ampere equation. Yeah. Okay. So because if we pull back down n forms, we get n forms and we can integrate those. So we naturally can consider functionals given by Monge-Ampere operators. And what we have seen in the case of L beta is general, right? So if I take arbitrary n form and consider this functional on M, then the corresponding variational problem is phi satisfies this equation, right? The corresponding variational problem is solved by phi if and only if this Monge-Ampere equation is solved by phi. Okay, and this omega equals L beta is a special case, which has this nice expression. Okay, and so sorry, I used Lagrangian density here a few times, but I wanted to call it this way. This is the proper definition that I want to use. And simply, if I take n form on J1M, I call it a Lagrangian. And the first order Lagrangian is a n form such that this guy, which is an n form on M, depends on phi up to the first order. So the coefficients, the coefficient functions of the n form depends, I mean the function itself, right? Because it's an n form on M, so depends on phi up to the first order. Okay? And now, in fact, so why do we introduce this notion, right? Because I want to have an equation on M defined for a function from M to R, and I ask whether I have Lagrangian with respect to M, right? Not, I mean, like the whole thing must be, if I pull back everything down on M, it must make sense in this setup. And so I'm asking which kind of forms on J1M correspond to first order Lagrangians in the classical sense on M, right? And in fact, this guy is the most general thing that we can cook up on J1M, which gives you, if it is pulled back down, it gives you something which will depend on phi up to the first order at most. So in fact, this epsilon L beta, which we saw once again, satisfies this nice property, is the most general thing that will produce first order Lagrangians down on M. So we can fix to this simple n form. L, a function J1M, and simply dq1, dqn. And second lemma that we use is the coordinate expression of E L beta, Euler operator applied to L beta. This is n form again on J1M, right? And it looks like this. So beta mu here, everything should be clear here. Only I recall that, or remind that beta is this dq1 that's dqn, and beta mu is contraction of beta with the q partial q. Okay, so this beta mu, so say beta 1, would be dq2, dq3 up to dqn. Beta 2 would be minus dq1, dq3 up to the dqn. Yeah. Okay. And now the proposition, the necessary condition for solvability of the inverse problem is the following. If I take an equation, this is a equation on M, right? And L, you see now I have Q mu phi phi mu coordinates, so it's not a function of J1M. It's down on M. This will be a local solution of the inverse problem for this equation if 5 is satisfied for some non-vanishing function k. So I have two things to take care of when describing partial differential equations via differential form. Firstly, whether the form is effective, because the non-effective parts contain some vanishing terms. And secondly, I can, of course, because I'm interested in the equation itself, I can multiply the form by arbitrary scalar, and I mean, like arbitrary non-vanishing function, it will still be the same thing. Yeah. But in the problems that we will be seeing, we can always fix k to be 1 without loss of generality. So if I take equation, firstly, I want to find some differential form with which I can describe the equation as a Monjumper equation in this sense. If the form is not effective, I compute the effective part, and then I compare it with the general expression for EL beta. So I have an equation down on M. I represent the equation with a form on J1M, and then I know that it must be equal up to the multiple of by non-vanishing function with EL beta, because L beta is the most general thing which produces first-order Lagrangians. And also I know that EL beta, the Monjumper equation of EL beta, will be the Euler-Lagrange equation for L itself. And that's the main tool that we are using here. So let's see this example. Phi 11 minus C phi 22. So we are in this setup, we consider like two base coordinates, but one of them we consider as a time, right? And I have this equation 6. And of course, probably everybody knows that there is a Lagrangian for this equation. And just let us see how in this simple case the calculus works. So this form omega is exactly the guy such that if I consider the Monjumper equation for this omega, I will get 6. Yeah. So we can check it directly, right? Because if I consider the pullback of this, say of this first term, minus C dq1 wedge dp2, then I can distribute over the wedge, and essentially I'm pulling down on the dp2. And because d commutes with the pullback, I'm computing d of the pullback of p2. Pullback of p2 is the derivative of phi in the second direction, phi 2. And the derivative of phi 2, the exterior derivative of phi 2, is phi 21 dq1 plus phi 22 dq2. But I'm wedging here with dq1, so the first term doesn't apply here. And I get minus C dq1 wedge phi 22 dq2. Right? And similarly for this term, I get minus dq1 wedge phi 11 dq1. If I flip dq1 with dq2, I get plus here. And then if I take, then the whole expression will be in dq1 wedge dq2, and I will get precisely phi 11 minus C phi 22, the whole thing multiplied by dq1 wedge dq2. So if I let it equal to 0, then I know that phi 11 minus C phi 22 must be 0. Okay, so that's why this form represents this equation with respect to the Monjamper operator. Okay? And we see the computation here. So in this case, this form is effective immediately. It's not always the case that you guess the form and it's effective immediately. It's usually not, but in this case it is. Because if I contract with the partial u, I don't have any du coordinate here. So it's immediately 0. And if I contract with del q1 wedge del p1 plus del q2 wedge del p2, which is exactly what this bottom operator does, I get this expression. And that's 0 as well. Yeah, because contraction of dp2 with p1 is 0. Of course, dp is a dual to del p, right? And dq is dual to del q. So this form is effective. And if n equals 2, beta equals, the general beta is dq1 up to dqn. So n equals 2, we have dq1 wedge dq2. And if I contract dq1 wedge dq2 with del q1, which is this beta 1, I get dq2. And similarly, if I contract dq1 dq2 with del q2, I get minus dq1. As I said in what is 5? 5 is this condition that two forms, one form, another form, determine the same equation if they differ by some non-vanishing function. And this will be the necessary condition for the existence of L. We can fix K to be 1 without loss of generality. Of course, if we pick different K, we get, our corresponding multiple of the solution. And if we compare, what do we want to compare? Omega E with E L beta. Omega is this guy. Because it is effective, it is equal to its effective part, right? So I'm comparing this guy with this guy, 4. And since omega doesn't contain dq1, dq2, yeah, I don't have any dq1, dq2, I know that this whole thing must be 0. This whole bracket must be 0. Also, some other guys here must be 0. And if you write it down, we get the following set of conditions. That the second derivative of L with respect to P1 is -1, with respect to P2 is C, and that derivative with respect to U and Q is 0 for all mu. And we can solve this condition with this L, which after pullback is the classical Lagrangian, probably is well known to everybody, right? And so this J1 phi star L, which is simply this L substituted with P1 and P2 substitute phi 1, phi 2, is a solution to the inverse problem. Okay, so the conditions are not violated, and we are lucky we can guess L, which satisfies the conditions to get the Lagrangian. If we consider now a more complicated case of 7, so this is a dimension 4, then there is no such L. How do we see that? We determine omega, firstly, which represents the equation. The omega is this. This is the guy. If I pull back down along, if I consider the Monjamper operator with respect to this omega and let it equal to 0, the corresponding Monjamper equation, I get exactly 7. But this guy is not effective. We can compute the effective part. And it looks like this. Omega E equals 1/2 beta 1 wedge dp3, etc. Yeah. Again, we are in dimension 4, and beta 1 is, in this case, dq2, dq3, dq4. Yeah, so for example, this first term, beta 1 dp3, is responsible for if pulled back down, it will be something like 531 minus 513. Sorry, 531, and that's it. So this would be 531 term, and so on. So now we again compare omega epsilon with EL beta, and we see that these terms in the bracket with 1/2 are of this type. But in this EL beta expression, there is no term of this kind. And this is an obstruction, because we cannot get rid of this term, because the effective part of a form that represents the given equation is unique. Right?
But couldn't it be that you just started with the wrong omega?
No, it could not, because all the omegas that represents the same equation are differing so in order for a different omega to also determine the same equation, I can compute the effective part again, and those two effective parts must differ by a scalar multiple. You see? So if I take different omega, the omega epsilon would pop out in this way, but with different scalar here somehow. You see? So it's not a matter of choosing this omega. This omega can be chosen arbitrarily. Whether it is effective or not is second question. But then I can determine the unique effective part. And if I take two different omegas and two different, and I compute the effective parts, they must differ by a scalar or a non-vanishing function, multiple by a non-vanishing function, because they represent the same equation, and they do not contain any vanishing terms in their expression.
But by a vanishing function, non-vanishing function, do you mean something that only depends on the q's, dq's? So they're both four forms, I guess.
Yes. They are
both four forms. So,
yes.
So you say the difference is, how can a difference then be a function?
Well, the difference between the starting omegas, is not a
four form.
Yes. But I mean, sorry, not difference. But I mean, like the one effective part of the one form would be a functional multiple of another, of the effective part of the second form. You see?
They have to be proportional. Is that what you're saying?
Yes, that's what I'm saying.
Yeah, that's probably not clear to me.
So the argument is as follows. If you take a form that represents the given equation, then there are two things that you can, I mean, there is a whole class of forms that can represent the given equation. And in this class, there is a unique up to a non-vanishing function multiple in this given class, and this effective part can be computed, which represents the equation, right? there is no other way that you can. There is no other things that you can change about the form itself without changing the equation. Once we have the effective part. Does that answer the question better? I'm not sure.
That's because when you are trying to figure out what kind of equation the form gives you, you have to use the Monge-Ampere operator, right?
Yes.
And it only talks with the effective parts, and after you apply it, you get the top form, and top forms can, differ only by functions, right?
Yeah, but the fact that the effective parts of a given form, you see, this effective part is also a form on J1M. So in fact, you get the statement holds on J1M or on the space of forms of over J1M.
Yeah.
This where do we have it? This here, this one. Right? Because if you want to have, say you have a form that represents a given equation. If you want to change this form in some way which is not by multiplying it by non-vanishing function, then the only thing that you can do is to run through the class of forms that represent the equation, but this class is given by essentially adding either the so the difference that you will get will always contain the difference of the two forms representing the same equations if expressed in the same coordinate system. The difference will always contain the terms that are vanishing on the Monge-Ampere operator. And that's the reason why the effective forms are introduced, to get rid of these vanishing terms.
Maybe it's also good to comment that this is when you represent your equations just as differential forms, not as just, an equations, a set of equations, you are basically dealing with the strong inverse problem, not the weak inverse problem, in which you could also multiply by a non-degenerate matrix.
True that.
And you could have found a Lagrangian maybe in this case, but that's not what you are doing here, because I don't think it is capturable by this formalism.
Yes, exactly. So I'm not sure whether I clarified it a bit more or not, but you can ask further questions if you want.
Can I just ask out of interest? You said it last time, but how exactly is the Plebanski? What is the Plebanski equation or the?
So what we are dealing with is a real Plebanski equation. I mean, the original first and second Plebanski equations are given by self-duality and anti-self-duality conditions over a complex four-dimensional manifold. Yeah, that's where the equations pops out. And we take their real version. We simply assume that the functions are real, depending on real variables and having codomain real numbers. Yeah, but those are, I mean, duality and self-duality conditions over four-dimensional complex manifolds in general relativity. I can link the paper of Plebanski where it is derived, if anybody is interested.
Yeah, sure. You don't have to do it now.
Okay.
You can do it.
Okay. Okay. So in a similar fashion, we can take other equations. This was the second row is second Plebanski, the first row is first Plebanski. And then this is a Grand equation and a Husain equation. And those equations also come from some cell duality or anti-cell duality conditions. And it's possible that because of they are coming from some cell duality or anti-cell duality conditions, that's why they do not have Lagrangian in this setup, right? But none of them has. Now there is a shorthand notation, but it's quite simple. If you see D with upper index, the upper index denotes the DQ, and the lower index denotes the DP. So for example, D1 to upper and 1 to lower means DQ1 wedge DQ2 wedge DP1 wedge DP2. So there are 2 Qs and 2 Ps in this omega P1. And depending, of course, what number we have, appropriate DQ or DP is considered. So those are forms that if you consider the Monge-Ampere equation for these forms, you get the left-hand sides, I mean the left part of the table. And none of them is effective. The effective parts looks like this. Yeah. And all of these 4 forms, all of these omega P1E, omega P2 E, and etc., they all satisfy that if you apply the bottom operator, it's 0, and they are vanishing along the read field. So according to the Hodge-Lepage-Lichagin decomposition, they are unique for this given omega P1, omega P2, etc. But these 2 forms do not vanish with the bottom operator, so they are not effective. But if I have omega P1, and if I have omega P1 epsilon, and I consider the Monge-Ampere equation, it will be the same equation. And as we have seen in the case of second Plebanski here, this DQ3, DQ4, DP1, DP2 was an obstruction term in order for the equation itself to have Lagrangian, such that the equation is Euler-Lagrange equation of the Lagrangian. And in the rest of the cases, it'll always be so, but there'll be much more terms. You see all these D1 to upper, D1 to lower, and similar terms. They are not included in the EL beta, in the most general form that we can have. You see, you always have only one DP. So the corollary is that all those 4 Monge-Ampere equations do not correspond to a variational problem of a first-order Lagrangian function. But interestingly, if we split the equation into an evolution system like this, so you single out one variable, you can understand this as time, for example, and you introduce a new function such that this function is a time derivative of the original field phi, then the second equation will look like this. So the system 9 is equivalent to 8. And this system has Lagrangian. And this is the Lagrangian. But the Euler-Lagrange equations that give 8 are 1 order higher. If I want to reproduce from this guy, this system 9, which is equivalent to 8, I need to use 1 order higher derivatives. So what it means is that the generalization for true fields, what we can do is we can proceed similarly as we did in the case of one field and define multiple Euler operators in a completely similar fashion. Just we have not one contact form, but more contact forms. We can consider the exterior derivatives. They won't be symplectic forms on the corresponding distribution because the dimension doesn't fit well. But they will be symplectic forms on some restricted space. But that's the question whether then it can be work out nicely. But even if everything works, we will only get all your Lagrange equations which ends with this terms del q mu, right? We will not be able to reproduce this higher order terms in the Euler Lagrange equations. So let me just show you briefly what I mean. So instead of the bundle M times R M times R to M, we may consider M times R squared to M for two fields, and then consider the jet bundle for this projection. And as I said, we can introduce, so let's say this is for two fields. We can consider in a completely similar fashion, instead of just C, we have C1 and C2. And when I see P, it's a derivative for the first field. And if I see R, it represents the coordinate for derivative of the second field. And U is for the field itself, V is for the second field itself. Then I have the corresponding omega I, and I have the corresponding operators bottom I, and I have two Reeb vector fields. Oh yeah, and I have two projection operators, and I can consider two Euler operators. And really, if we compute in local coordinates how this looks like, they will give this system for phi and for psi. But you see the terms, the higher order terms are missing. So this approach, although if we consider the composition for the second Plebanski, like this, then we have Lagrangian, but the naive method of extending the above method to more fields will not work here. So yeah, well, that's the drawback. Hard to say whether it can be done in some nice way to produce the higher order terms, but it's not definitely in some straightforward way, because it's not like that if I compute the Euler operator multiple times that it will produce Euler Lagrange equations of higher order. It doesn't work this way. Okay, and so
sorry, can I ask about this? I'm a little bit confused.
Yes.
So you have two approaches in which you can, let's say, bypass the fact that the second Plebanski equation doesn't give you a Lagrangian. So here you showed that you can split the equation into a system of two equations. You add a new field, and then you can find a Lagrangian. But Lagrangian is still it still has second derivatives in it, right?
Yeah, it is not the Lagrangian in the, yes, exactly.
So it's on J2M.
Yes, exactly.
And could you
it's a different thing. It's a different thing. Yeah, that's just a comment of. I mean, you have also said it maybe even multiple times the last time, and today at least once, that we can find the Lagrangian if we go to high enough jets, right? So that's something that happens here.
Yeah, well, yeah, but what I'm confused about is that just you are doing two things at once, right? You are splitting this equation into two, adding a new variable, and also going into higher jets. So could you not have just gone into higher jets and solve it without a new field?
Yeah, but that's the problem, that if you go to higher jets, you don't have the structure that I'm using in the previous approach, because again, what we are using here all the time is that the distribution given by the kernel of the contact form is one codimensional. And if I go to higher jet, it will not be it will no longer be true. So I won't have the same setup at all. You see?
Yes, I see, but does this
I don't know. I don't know whether it can be fixed somehow, yeah, or how does it work for
I
higher
understand.
jets, yeah. I know that that people are working with infinite jets, and I think that I can recommend some papers from how is he named? Well, sorry, I can't remember the name, but people already, I think, solved some version of the inverse problem. If you go to infinite jets, then always you have a solution. But I'm not completely sure about the assumptions. Yeah, so I can give you some readings, but not very very sure about what the details are there. Yeah.
Yeah. Okay. Thanks.
Okay, so I will end here. So what we can do, we can define a multisymplectic form, but maybe take it very lightly, this part. I thought it will be more interesting, but the only thing so far I managed to do is to really construct the multisymplectic form for given equations. But this approach is not the same as multisymplectic formulations by, for example, Frederick Helene or Husain or other people that are trying to, Narciso Roman Roy, I think is the other guy who is quite involved in this stuff, who are trying to formulate certain differential equations, partial differential equations via multisymplectic formalism, and then producing Hamiltonian, because in their approach, they always start with, or at least as far as I know, they always start with the case where there is a Lagrangian, right? This theorem gives you a multisymplectic form in arbitrary case. Once you are able to represent the equation by differential form, you can always compute the effective part. And if the two conditions are satisfied, then you are able to construct a multisymplectic form. And it is of this type. Yeah, it's over J1U times R trivial line bundle over J1U. In all our cases, this is satisfied, both conditions. The second condition is easy to see because all forms that we used are constant coefficients forms. So it's immediately seen that the projected derivative will be 0 on them. And to show that they are linearly independent is that this set, yeah, which is constructed by take your effective form omega. Yeah, see, we assume effectiveness in the very beginning. Take your effective form omega and contract it with all q's. For each q, you get one element. In the case of 4-dimensional equations, this will consist of, this set will consist of 4 elements, and each element will be a 3 form. And in all the cases that we have, the set is obviously linearly independent. So for example, for the first Plebanski, the set looks like this. And so this is the construction of the effective part of, or effective form representing the equation of Plebanski, the first one. This x, y, z, w are quite whatever because we cannot get, I mean, they are of different type than this D2, 3, 4. They are always of 1 index up and 2 index down. So it will be something like always dq wedge dp wedge dp. And so you cannot get rid out in any way of these terms which have 3 indices up and are obviously different in all the 4 elements. So for example, in this way, you can see that this SP1 is linearly independent. And in a similar fashion, it works for SP2 or this set for Grant or Husain equation. Yeah, so always the first condition in the cases that we are dealing with, this first condition is always satisfied, and the second condition is immediately seen to be satisfied because all the forms that we are using are of effective forms that we are using are with constant coefficients. Okay, so that's more or less what I wanted to say. I have a feeling that it was a bit confusing. I'm sorry for the initial confusion about the notation, I guess, more or less. I wasn't considering transformation rules on the first jet space, so that I cannot say by heart that that is a real issue or not. But hopefully it got a bit clearer after the discussion. And I guess that's it. So I hope you enjoyed at least a bit, and if you have any questions, I'm open. So thank you for your attention.
Yeah, also thank you. It was very nice. So yeah, please, if anyone has any questions, you can go ahead and ask. Yeah, maybe I'll start just by asking, is this something you are currently working on, or are you planning to do something like this in the future, or about this multisymplectic stuff?
Yeah, definitely. I want to see whether this generalization into more to the case of more fields, whether it can be somehow used, because well, at least it's interesting that that going the naive way, you can reconstruct the Euler equations for more fields, yeah, quite directly. It seems that there is some categorical structure involved, some direct product hidden in the construction. So that's interesting. And also, I would like to know how the multisymplectic stuff can be used in any interesting way.
Mm-hmm.
Yeah.
Yeah, I know about the work that Jana and Olga did, and they basically, well, I'm not sure if they managed to prove, but they were at least very close to proving that you can find generally a Lagrangian to any equation if you allow for this weak inverse problem, when you can multiply the equations by an arbitrary non-degenerate matrix, some functions, so that basically you are not interested in the equations itself, but maybe in the system of the solutions, that you want that to be preserved. But I believe they don't use the same formalism as you do here. So I think it might be interesting to look into that and see what is the difference, and because I'm not sure if what you're doing here could also be applied there. Maybe it could, and it would be interesting to see that, but I think they were using more like brute force methods, not very sophisticated. So maybe it would be desired to check that out.
We should have invited Jana to join us.
Yeah, I don't think
I saw her going on the corridor.
Yeah, maybe we can, me and you, Radek, we can set up a talk with her later.
I was definitely thinking about speaking with her about this, because well, it might be quite interesting discussion.
Yeah. Yeah, so do we have any other questions or comments? Yeah, well, if not, then I guess we can